Okay, we are going to start this session for young researchers with Alba González Vega. Alba is a PhD student at the Spanish Institute of Oceanography in Tenerife, Canary Islands. She's interested in the effects of submarine volcanism and hydrothermalism on the physical and biogeochemical properties of the marine environment, and her research has focused mainly on the recently formed submarine volcano Tagoro at El Hierro, Canary Islands. Her talk today is entitled The Submarine Volcano Tagoro, Physical Chemical Changes in the Marine Environment. So Alba, the floor is yours.
Today I will be talking about the submarine volcano Tagoro at the island of El Hierro and the physical and chemical changes that it has caused in the surrounding marine environment during its 11 years of life. Well, okay. So I will talk about 3 different studies that we have carried out. 2 of them are already published and the last one is in the process. So first, the first one is about the lack of oxygen or deoxygenation that occurred during the eruptive phase of the volcano. The second one is about the emission of inorganic nutrients that happened both during the eruptive and the post-eruptive stages. And the third one is about the physical dynamics that might be taking place in the area during the current post-eruptive stage. First, I will make a brief general introduction. We have been talking about Tagoro volcano today a lot, so I will be quick. As you all know, this is a volcano that erupted in 2011 south of El Hierro Island near the town of La Restinga. And just to go over some of the most important characteristics, the summit is at 88 meters depth, so it's a pretty shallow volcano. And that's also the secondary crater, and the main crater is a little bit deeper at 127 meters depth, and it has an irregular diameter of 1 to 1.3 kilometers. The history of this volcano can be separated into 2 phases. So first there was the eruptive phase, which lasted about 6 months from October 2011 to March 2012. And during this time, there were obviously lots of physical and chemical changes in the marine environment, very drastic. Eugenio talked a little bit about it before, so I won't repeat. For example, the temperature rise and the salinity decrease. The CO2 increased a lot, and therefore the pH dropped. And there was a big emission of reduced chemical species, especially of iron and sulfur, and this caused a reduction in the oxygen. And then since March 2012, the system evolved towards a hydrothermal system, which still remains active to this day, and we have hydrothermal vents spread around the main cones. Also with diffuse flow, and they are low temperature vents. Okay, before I start talking about the different studies, I would like to briefly introduce what are the sampling strategies that we have followed over the years in order to adapt to the behavior of the volcano and the spatial and temporal reach of the processes that were taking place. So as we get all our data from CTD casts with different physical and chemical sensors, and also from water samples from the Niskin bottles. But there are different ways that we can do this. The most basic and used way in oceanography is just doing hydrographic stations. So just in a certain point, the rosette goes down and up one time, and with this you can make a grid or a transect or whatever you need. But there are also other ways to do it. For example, we also do what is called yo-yo stations, which is the same as a normal station, but it's repeated many times in the same point, many times, like up to 100 times, in order to obtain a time series with very high time resolution. Then another technique that we use a lot is called tow-yaw. It's similar to the yo-yo in the way that you go up and down with the rosette, but at the same time, the vessel is moving at a slow speed. And this way we obtain this kind of sawtooth-shaped data set, which is very useful because it has a very high spatial resolution. So it's very useful at some points. And then finally, at some of our cruises, we are also able to collect samples with an ROV, a remotely operated vehicle. In this case, we use the Lirocus 2000 from the IEO. And with this, we are able to get samples directly from the hydrothermal vents with different instruments that we have developed for this specific purpose. And these would be like the most undiluted samples that we can get. Okay, so now let's dive into the first study. Like I said, this is about how the oxygen dropped during the eruption of Tagora volcano, and this has already been published this year. So first, to put you in context, what happens when there is an eruption underwater is that the volcano emits a lot of chemical reduced compounds, and when these compounds come into contact with seawater, they are quickly oxidized, and therefore there's a chemical consumption of oxygen. And this is why in volcanic settings there is often suboxic and even anoxic conditions. Here are some of the reactions that take place and that consume oxygen. Okay, so for this study, we use data from up to 13 different oceanographic cruises. But right now we are just going to focus on the ones that took place during the eruptive stage in 2011 and 2012. And in this case, the methodology that we use is only vertical stations forming a grid around the whole island of El Hierro, because at that time the eruption was taking place, and so there was a big area that had to be covered. And we used a continuous oxygen sensor mounted in the CTD, but we calibrated this data with over 3,500 water samples analyzed with the Winkler method. And we use this for calibrations, and the calibrations are generally very good. So this is a very robust data set. So now we can see finally some results. Here we see vertical profiles of oxygen with depth for the different cruises during the eruption. So the black line represents a reference profile, which is the normal conditions, outside of the affected area. And the red and blue profiles are what was measured in the area affected by the eruption. So here we can see that the oxygen dropped drastically. The lowest values we measured were close to zero, were 7.71 micromoles per kilogram. This represented a 96% decrease in oxygen respect to the normal conditions. So these were near anoxic levels. This plume of deoxygenated water had a very wide scope. So, for example, in these horizontal contours, we can see that we were able to determine a plume of around 378 square kilometers, but notice that the plume is not close in the border, so it was probably even wider. And the distribution of the plume was very variable because of the local currents or the strength of the eruption. So at times it reached even the north of the island. And here, for example, we measured an additional northern plume of 86 square kilometers. And like I said, the plume was very variable, but we estimate that at times it could be, the area covered could be more than 400 square kilometers. And just for comparison, this is almost twice the area of El Hierro Island itself. During the eruption, we were also able to follow an anticyclonic eddy that was formed at south of the El Hierro Island. This is a very common feature in the Canary Islands because they are an obstacle for the Canary currents. But this, this was a special one because we were able to follow it via satellite thanks to the discoloration in the water caused by the eruption. So we followed it and we sampled it at the center of the eddy when it was 80 kilometers away from the volcano. And even then, it still had a weak signal of deoxygenation. It was already small, of course, it was 8% decrease because it had been mixed and diluted, but it was still present even after an 8 kilometers journey of the eddy. And finally, this is just to show that in the post-eruptive state, the oxygenation is no longer observed. This is the data from all the cruises shown as anomaly, which means that if it's close to zero, it means that it's very similar to what we find outside of the volcano. So this is just to show that after the eruption ended, the oxygen levels came back to normal. Okay, let's jump into the second study that I would like to talk about. This is about the emission of inorganic nutrients from the submarine volcano. So the nutrients that we're going to be talking about are mainly nitrate, although this is a sum of nitrate and nitrite, phosphate, silicate, and also some data of ammonium, but we don't have that many data of ammonium. For this study, we used data from over 7 years of monitoring from 15 different cruises and over 3,300 water samples. So it's also a very robust data set. And the data were all analyzed with an auto-analyzer in our facilities at the IEO in Tenerife. So here the sampling was a bit more complex. Because at first in the eruptive stage and the first years of the post-eruptive, we did the same that I showed before, which was just a grid of vertical stations, first around the island, and then when the eruption ended, we focused more on the area around the volcano. But then we realized that in this post-eruptive state, the emissions stay closer to the seafloor, so we decided to use a new approach, which were the TOW, and this gave us samples that are much closer to the seafloor. And then finally, in a cruise in 2018, we were able to collect samples with ROV, which would be the most undiluted that we can get. And here are finally the results. Again, these are vertical profiles of the different nutrients, nitrate, phosphate, and silicate. Once again, the black line is a reference profile, so the normal conditions. And then the rest of the profiles are our nutrient data in the volcano using the different methodologies. I will just highlight the most important, which is that there was very important enrichment in all the nutrients. Silicate was the most dramatic one, with it was in the vent samples collected with ROV, it was more than 300 times the normal conditions. And then, of course, in the water column samples, which are in blue, obviously the enrichment is a bit lower, but still very important. And one thing I want to highlight here is that you will see that nitrate is a little weird because it's more concentrated in the water column than in the vent samples. And this is because nitrogen is actually emitted as ammonium, which had 98 times enrichment, but we don't have that many samples of ammonium. That's why we can't show profiles. These are the plumes of the inorganic nutrients emitted, seen as like a vertical section, and the plumes have around 400 meters diameter. And it's also important to notice that sometimes, depending on the time of the year, this plume can go through. I mean, it can reach the mixed layer, which is the first layer in the ocean, and also the euphotic zone, which is where there is enough light. And also, we did some calculations for the nutrient fluxes that would be exported using this vertical section and the data from the average current in the area. And I won't go into detail, just to let you know that these fluxes, when compared per unit of area, are comparable to some very important nutrient inputs in the area, such as the African coastal upwelling. Okay, and finally, we reached the last study. This one is still ongoing, but we are trying to describe what are the physical dynamics that are taking place in the area in this post-eruptive stage in the hydrothermal emissions. So I will jump right into the hypothesis that we are trying to study here. So the volcano emits hydrothermal fluids that are hot and have low density, and therefore they should rise, they should go up. But then as they go up, they start to cool down, they start to get more dense, and so there comes a time where they have to sink back again, and also to replace that water that was that went up. And so this forms these convective cells, or convective flow that is continuously going, supposedly. And I won't go into much detail with this, but this can also, maybe due to rotational effects, this can also cause an anticyclonic circulation around the convective cells and a cyclonic circulation underneath, but we're not going to go into much detail in this. We're going to focus on this convective flow. So this was widely described in the literature. Here I put some examples, but there are many more. There are models, there are data that support those models. There are also even some lab experiments, like you see in the last panel here. And if you look at the dates in the citations, you will see that this was a very popular topic during the 90s or late 80s and 90s. But since then, it hasn't really been updated. It was a little bit forgotten. So we would like to update it because it seems like this could be happening in Tagoro. So for this study, we used data from two oceanographic cruises. One took place in December 2020, and the other one in April of 2021. And here we did two things. First, we did a grid of stations, like we saw before, but this time it's very focused on the area around the main cones and with very high spatial resolution. And then we also did some yo-yo stations, which again is just repeating a station we did up to 80 times, and this took about 12 hours straight. And we did this in 3 different points around the volcanic cone. And also we did it outside for reference. Okay, so here we can start seeing some results. As always, we start with vertical profiles of different variables. Here we have density, temperature, salinity, and fluorescence for the 2 cruises, December and April. And as always, the black line represents a reference profile. And first of all, I would like you to notice the normal conditions in the area, how they differ from one station to the other. So in December, we have a very marked thermocline which starts around 100 meters depth. And above that, we have a mixed layer that is very homogeneous. Whereas in April, we don't have a very marked thermocline. It's either very weak or maybe it's deeper and we are not seeing it here. And there is, we can see that there's a lot more mix. So this information will be important later. And then the rest of the profiles, all the colors, are this grid of stations that we carried out. And what we did was that we represented the colors depending on the distance to the main crater. So for example, the red and oranges are the closest ones to the main crater, and so on. And so you can see that those first profiles sort of go above the reference profile, and then in the yellow to green area, it starts to show up below the reference profile. So so far, this supports the hypothesis that, it goes up and down, sort of. Okay, now here we're seeing the results of the yo-yo studies. That's why the x-axis is time and the y-axis is depth. And we're seeing different variables as anomalies, which anomaly is just the difference between what was measured there and what was measured in the reference station. Red is positive and green is negative. So there's a lot of information here, but first of all, what I would like to highlight is that, again, the difference between December and April. So in December, you can see that there are, there are lots of anomalies from around the depth of the thermocline, around 100 meters depth and below that. But above that, we don't see that many anomalies. Whereas in April, there are anomalies in the whole water column, and there you can see that there's more mixing. So this is probably because the thermocline is acting like as a barrier for the anomalies, so it can't go through in December, and so they stay below that. But in April, it's able to reach, the anomalies are able to reach the whole water column. And here you see that we're always representing physical parameters, but also fluorescence. Why is that? It's because fluorescence, because we want to address the question, because we've seen that the anomalies carry a lot of nutrients. So we want to address the question of, are these inorganic nutrients, enhancing or helping the primary producers? And fluorescence is a first approximation to that. It's an approximation to the chlorophyll in the water column. And that's why here we have also in this graph, the integrated fluorescence in the water column. This is again from the yo-yos. That's why the x-axis is time. And what we see here is that we have in the dashed line represents the integrated fluorescence in the reference station. So again, normal conditions, and the solid lines were measured in the volcano. And we see that in December, the integrated fluorescence in the volcano is kind of similar to the reference. Sometimes it's lower, sometimes it's higher. There seems to be like fluctuations. But in April, and this is the interesting part, it's always above. There's always more fluorescence, which means likely there's more chlorophyll, which could mean there is, the interpretation is more complex because it's not a direct relation to how many primary producers there are, but this is a first approximation to know that something is going on, and especially that it's very affected by seasonality. Okay, so to sum up all these studies that we've seen, first we saw how during the eruption there was a volcanic plume that was very deoxygenated, and it had a very wide width of over 400 square kilometers. And this low oxygen, along with the low pH and the high concentrations of CO2, were the reason why there was so much high mortality, and there was so many, all the ecosystem was really negatively affected in that first stage during the eruption. But then during the post-eruptive stage, we no longer have this deoxygenation, and we have, in a much smaller area, we have a plume that is very rich in nutrients, in inorganic nutrients. And so this started to raise the question of whether these nutrients have an effect on primary producers. And then finally, we are seeing that likely there is a recirculation in a convective flow that sort of traps these enriched waters. I mean, there might be some export, but there's also, you know, a recirculation, which also could enhance even more this fertilization effects. But we have seen that this effect is very strongly affected by seasonality and by the structure of the water column in each of the seasons of the year. So this is all I wanted to talk about. Thank you so much for listening. Here, if you want to read the publications that are already published, you can do it here. And yeah, I will be happy to answer any questions. Thank you.
Thank you so much, Alba, for your very nice and interesting presentation. Now it's time for questions, and we'll start here.
Hi, thanks a lot for your talk. I really appreciate your easy to understand explanations. I assume that you mostly focus on your study area, but do you know by any chance if the water depth of the vent has any control of or on what you observed? So assuming that or knowing that there's a gradient of oxygen availability in the water column, would you expect different results in different water depths?
Different water depths? No, I mean, this is a very, do you mean if deeper we would find also you know, anomalies, or sorry?
So I was thinking in a normal state we would have this gradient of oxygen in the water column. So if we have a vent at a different water depth, we have a changed availability of oxygen for oxidization of nutrients, for example. Would you expect that to have a control on the results that you observed in your case?
Yeah, of course, it depends. It depends on the you know, basal conditions of the area. In this case, it was a very oops, sorry. It was very special conditions because the volcano is at a depth where it's, you know, still again near the euphotic zone, near the thermocline. So there's a lot going on there. But yeah, for sure, the results would be different in a setting that was usually most of the studied volcanoes are deeper, and all these processes are completely different there.
Cool, thanks. More questions? Are there any questions in the chat?
You talked about the effect on primary producers a lot. Did you see a large alteration to the deal vertically migratory species?
Sorry, can you repeat the question? I didn't hear it.
Yeah. Did you see a large alteration to the deal vertically migratory species?
These studies have not focused on this. During the eruption, there were studies about all the communities. There was the zooplankton communities were very affected, and the migration was very affected. There's one of the papers that really talks about this. But my focus is not on the biology. So again, now that we know something is happening with the biology, now is when we have to start making more specific studies. There's also one paper about the zooplankton during this post-eruptive stage, which shows that there is a difference in the community structure in the volcano respect to the outside, and that is also very interesting. But yeah, these studies have had a more physical and chemical focus.
So no more questions, no? Then we jump into the next speaker, Juan Pablo Martín. Thank you, Alba. sorry.
Thank you so much, Alba.
Thank you.